our universe, vast, mysterious, and awe-inspiring. For millennia, humanity has looked to the skies, seeking to understand the secrets of creation. Today, we embark on a journey beyond the edge of time itself. Welcome to Eyes on Bharat, where we explore the interplay of ancient wisdom and modern discovery. In this special episode, we unravel the enigma of a possible cyclical universe, a concept that resonates in the sacred Vedic texts and find echoes in cutting-edge physics today. Did the universe truly begin once, in a single Big Bang, only to expand indefinitely? Or is there a more profound cycle, one of repeated birth, growth, and dissolution, mirroring the rhythmic dance of night and day? The Vedic tradition suggests the latter, describing cosmic cycles on timescales so vast they boggle the human mind. Meanwhile, modern theories from the Big Crunch to the Big Bounce are beginning to entertain a strangely familiar idea that our cosmos might have existed many times before and may do so again. In the vast tapestry of Hindu thought, the universe does not simply appear once and vanish. Instead, it moves through the endless cycles of birth, preservation, and dissolution, Srishti, Sthiti, and Pralaya. These cycles, described in Vedic and Puranic texts, suggest that cosmic time is a wheel turning without end. Central to Vedic cosmology is the concept of 4 yugas or epochs, each with its own defining characteristics and length. Satyuga, often called the Golden Age, said to last 1,728,000 years. It represents a time of dharma, perfect virtue, and wisdom. Next, Treta Yuga runs for 1,296,000 years. Followed by Dwapara Yuga for the next 864,000 years. Finally, our current era, the Kali Yuga, lasts for 432,000 years. In each successive yuga, human virtues diminish and lifespans shorten, reaching their lowest in Kali Yuga. Together, these 4 yugas form one Mahayuga, totaling 4.32 million years. This is just the beginning. Now let's go bigger. A single day of Brahma, known as Kalpa, spans 8,000 Mahayugas, or about 4.32 billion years. When Brahma Day ends, partial dissolution ensues, known as Pralaya, and the cosmos temporarily recedes. After Brahma's night, another cycle begins, and the life is remanifested. One day and one night of Brahma together make 8.64 billion years. Multiply that by 360 and you get Brahma's year. Expand that to 100 Brahma's years and we arrive at the unfathomable timescale of Brahma's lifetime, at which point a total cosmic dissolution, Mahapralaya, takes place. These numbers dwarf our everyday sense of time. They remind us how ancient seers visualized cosmic durations that challenge even modern imagination. Vedic texts often describe this repetitive process as the universe breathing, inhaling during dissolution and exhaling during creation. It's likened to the breathing of Mahavishnu in some traditions, emphasizing that creation isn't just a one-time event, it's a cosmic heartbeat pulsing endlessly through existence. The parallels to modern cosmological theories such as the Big Crunch or the Big Bounce are striking. While today's physics speaks in terms of singularities and universal collapses, the Vedic poetically framed this as the dance of the divine, an eternal interplay of birth, death, and rebirth on a cosmic scale. It's important to note that these immense timescale and cyclical narratives reflect a worldview steeped in symbolism, devotion, and a recognition of higher cosmic intelligence. From a purely spiritual perspective, it underscores an eternal framework in which souls travel multiple lifetimes across vast epochs, each yuga offering unique challenges and moral arcs. For decades, scientists have probed deep space, seeking clues about how our universe began and how it might end. Our current mainstream understanding stems from the Big Bang Theory, which suggests the universe originated about 13.8 billion years ago from an extremely hot, dense state. As it expanded, matter coalesced into galaxies, stars, and planets, leading eventually to life as we know it. But here's the question: does the universe expand forever, or might it reverse course, leading to another beginning? Several modern theories propose that what we perceive as the start could be just one phase in an eternal cycle. Instead of an initial singularity, the Big Bounce hypothesis envisions a prior cosmos, that collapsed and then bounced into expansion, avoiding a total breakdown of physics. In loop quantum cosmology, gravity becomes repulsive at extremely high densities, so a contracting universe reaches a tiny finite size and then rebounds outwards. This replaces the Big Bang's something from nothing with a rebound from previous phase. The idea dates back to early oscillatory universe concepts. But those faced entropy problem. Each cycle would accumulate heat and grow longer. The discovery of dark energy offers a possible solution by allowing each cycle to dilute entropy. In fact, the presence of dark energy provided a new hope for a consistent cyclic cosmology. By stretching out and cooling the universe before a recollapse. Variations of the Big Bounce appear in different frameworks. Example, loop quantum gravity's bounce, or an extension of general relativity with torsion that naturally averts singularities. In the Einstein-Cartan approach, spinning matter in a collapsing universe creates torsion that causes cusp-like bounce at high density, avoiding a true Big Crunch singularity. All these models replace the absolute beginning with the previous cosmic phase, potentially one of an infinite series of cycles. In string theory and brand cosmology, another cyclic tale unfolds. The Ekpyrotic model was developed by Paul Steinhardt and Neil Turok as an alternative to inflation. It imagines that our observable universe lies on a three-dimensional membrane floating in a higher dimensional space. A second brand, parallel to ours, exists in this higher dimension. Periodic brand collisions play the role of the Big Bang. In each cycle, two brands are drawn together, then collide. The tremendous energy of this collision is converted into the hot matter and radiation of a new Big Bang on the brane. After the collision, the brands recoil and our universe expands for billions of years. Gravity eventually slows and reverses the expansion, starting a gentle contraction again. This leads to another collision and bang, and the cycle repeats indefinitely. A remarkable feature of the ekpyrotic scenario is that it can solve the same cosmological puzzles inflation was invented for: horizon, flatness, etc., but in a very different way. The slow contraction before each bounce naturally smooths the universe and dilutes irregularities, and the interplay of the brands can explain why our universe has no monopoles and why space appears flat. Quantum fluctuations during the approach of the brands could seed the galaxies and cosmic structure observed after the bang. Unlike a traditional oscillating universe, the ekpyrotic cycles need not suffer from ever-increasing entropy. During each immense expansion, the universe has a net increase in volume. In short, the ekpyrotic model paints a picture of cosmic phoenix. Each universe is born from the fire of a brand collision, lives out its eons, and then its ashes sets the stage for the next universe when the cycle repeats. In mathematical terms, cosmologists often refer to the Friedmann's equation derived from Einstein's general relativity, which describes how the universe's scale factor AT evolves. For a closed universe with enough matter density, the scale factor may reverse, leading to a contraction phase, a crunch. If a certain quantum conditions allow, this could transition to a new expansion, a bounce. While these scenarios remain theoretical, they challenge us to envision a universe where the time may be cyclical. Proposed by renowned mathematician Roger Penrose, CCC is an elegant but radical cyclic model. It posits that the future of our exponentially expanding universe can be rescaled to become the Big Bang of a new universe. In this picture, each eon of the universe begins in a hot, smooth Big Bang and ends in an extremely cold, empty state dominated by light. Once everything is essentially massless radiation, time and distance lose their meaning. That point becomes the next Big Bang. Thus, Penrose's cosmos is a daisy chain of universes, each conformal to the next. Black hole evaporation in one eon seeds tiny imprints in the next. Penrose called these traces Hawking points after Stephen Hawking's black hole radiation. Unlike the Big Bounce, CCC doesn't require a physical contraction. Instead, it exploits geometry and thermodynamics to glide from one universe to the next. Penrose admits it's an outrageous idea, but it's motivated by the desire to explain the uncanny smoothness of our Big Bang without invoking an inflationary phase. Instead of an inflation smoothing the universe after the bang, CCC says the universe was already uniform before the bang, as the end state of the previous eon. This model, while intellectually fascinating, demands that currently understood physics behave in unfamiliar ways over ultra-long timescales. Cyclic universe models are intriguing, but is there any evidence that our cosmos had a prior cycle? This is the challenging question. Any previous universe would leave only subtle fingerprints, if any, in our observable universe. Cosmologists have nonetheless proposed ways to seek supporting evidence. The CMB, the faint afterglow of the Big Bang, is a natural place to hunt for hints of a pre-Big Bang era. If our Big Bang was influenced by a previous universe, it might show up as strange patterns in the CMB's temperature or polarization. One prediction from the Penrose's conformal cyclic cosmology is the existence of concentric circles of unusually low variance in the CMB temperature, possibly left by gravitational wave burst or black hole mergers from the earlier eon. Another expected signature is the aforementioned Hawking points, tiny hot spots a few degrees across, slightly warmer than their surroundings that could be final evaporations of massive black holes from the previous universe. In 2010 and again in 2018, Penrose and colleagues claim to have found the evidence of such features in data from WAMP and Planck satellites. For example, they reported several circular spots with temperature anomalies that were statistically unlikely in simulated random maps, arguing this is a strong backing for CCC. These announcements made headlines as potential glimpses before the Big Bang. However, follow-up analysis by other scientists have been largely skeptical. When the Planck team and independent researchers took a closer look with more advanced methods, they found that the supposed concentric circles could easily arise from random noise and the normal distribution of hot-cold patches in the CMB. After removing known artifacts, no statistically significant concentric rings or anomalous point sources remained in the CMB data. In the words of one analysis, no distinct features attributable to a previous eon were detected, meaning the CMB, as far as we can tell, is consistent with originating from a standard Big Bang with quantum fluctuations. Even purported Hawking points seem to disappear under rigorous scrutiny. So far, there are no bruises in our universe, no repeating patterns, no concentric circles of irregular fluctuations, no Hawking points, as one cosmologist put it bluntly. It doesn't mean cyclic cosmology is wrong, but if clues exist, they are subtle and require more sensitive observations. Upcoming missions with higher resolution or novel analysis techniques are continuing the search. Gravitational waves are ripples in space-time, and they can travel to us essentially unimpeded from the very early universe. This makes them a promising probe of any pre-Big Bang physics. Importantly, many cyclic models predict a very different gravitational wave signature than inflation does. Inflation typically produces a faint background of primordial gravitational waves, and these would imprint a specific pattern in the CMB's polarization. It's a calling pattern known as B-mode polarization. Cyclic models like Ekpyrotic Universe, on the other hand, generally predict a little to no primordial gravitational waves from their slow contraction phase. In fact, a key selling point of some cyclic models is that they naturally have an extremely small tensor signal. This contrast sets up a clear test. If astronomers do detect a primordial gravitational wave background, it would strongly support inflation and rule out most cyclic scenarios. Conversely, if no such signal is found, even with very sensitive experiments, it opens the door for cyclic models as viable alternatives. The race is on. Specialized telescopes at the South Pole and elsewhere are all searching the sky for the inflationary Bay mode fingerprint. In 2014, a team using Bicep 2 thought they had spotted it, causing a huge stir, but later it was shown to be dust interference. As of now, no conclusive evidence of primordial gravitational waves has been confirmed. The latest Planck satellite data combined with ground experiments have set very strict upper limits. The primordial signal, if it exists, is extremely faint. This non-detection is actually consistent with cyclic models' expectations. Upcoming experiments within the next decade will push the sensitivity further. Scientists predict we're nearing the capability to either detect a faint Bay mode pattern or declare it below detectable levels. If a clear B mode is found, it would be a smoking gun for an inflationary Big Bang, forcing most cyclic models back to the drawing board. If it isn't, as one researcher notes, it could undermine slow contraction and lend support to the idea that the universe had a different beginning than inflation suggests. Apart from the CMB, scientists are also trying to detect a stochastic gravitational wave background through other means. A characteristic spectrum of gravitational waves could hint at a bounce. For an instance, some bounce models predict a blue-tilted gravitational wave spectrum differing from inflation's predictions. These efforts are just starting, and no definitive signals from a prior cycle have emerged yet. One reason evidence is so elusive is that a cyclical universe might reset itself in each cycle. In many models, whatever came before the Big Bang gets largely wiped out by the extreme conditions of the bounce. It's a little like asking if you can find ashes of a previous forest fire in the new forest that grows afterward. Maybe some trace elements in the soil, but the new trees won't form recognizable patterns of the old ones. Similarly, any imprint from a past universe would likely be very subtle. Penrose's CCC offers a rare concrete prediction, specifically because in that model, certain radiation effects can carry over. Most other cyclic models like the Ekpyrotic model are constructed to avoid messing up with the next cycle. They want to start each Big Bang in a clean, smooth state. That means they often predict almost no observable residue of a previous cycle beyond the distribution of primordial perturbations. Another challenge is that our observations only go back so far. The CMB is a snapshot of the universe roughly 380,000 years after the Big Bang. Before that, the universe was opaque to light. To directly see into the Big Bang or earlier, we need to use neutrinos or gravitational waves or some other messenger. Neutrinos from the first second of the universe permeate space, but they are incredibly hard to detect. Gravitational waves, as mentioned, hold promise, but require extraordinary sensitivity. In short, searching for evidence of a prior cosmic cycle is a bit like forensic science on universe. We are looking for tiny clues, and it's easy to be fooled by mundane causes. Despite the challenges, these tests are crucial. They ensure cyclic models remain scientific, testable theories rather than just philosophical musings. As technology improves, who knows? A future observer might one day detect a clear ring in the sky or a specific gravitational wave echo that shouts before the Big Bang. Until then, the cyclic cosmologies remain compelling possibilities, awaiting either supporting evidence or a definitive falsification. Interestingly, such speculation resonates with the ancient Vedic notion of cosmic cycles. As we have seen, the sages described creation and dissolution not as finalities, but as repetitive, timeless rhythms. Are we on the cusp of uniting this ancient wisdom with modern physics? From ancient ashrams to modern laboratories, one thread unites these seemingly different worlds: an enduring fascination with cosmic cycles. How do we begin to reconcile the Vedic notion of repeated creation and dissolution with advanced physics and mathematics? Both traditions speak of time on a truly grand scale. The Vedas introduce cycles spanning billions, even trillions of years. Modern cosmology pinpoints a universe around 13.8 billion years old, yet increasingly entertains theory that suggests the Big Bang might not be the absolute beginning. Though separated by millennia, these perspectives share a certain reverence for renewal, the idea that existence isn't singular. Interestingly, luminaries like Carl Sagan once noted how Hindu cosmology's vast timelines were closer to scientific estimates of cosmic age than many other mythological systems. In modern physics, the drive to unify quantum mechanics with cosmic scale phenomena opens new doors. Could the cyclical models of the universe might be more than philosophical speculation? Some researchers believe so. At the core of this convergence lies an epistemological bridge. Vedic cosmology sees a conscious underpinning cosmic intelligence driving creation and dissolution. Modern physics emphasizes natural laws verified through observation and math, yet edges ever closer to ideas of cyclical time. Despite differing worldviews, spiritual versus empirical, both attempt to describe the nature of reality and our place within it. While science demands further evidence and ancient wisdom speaks through allegory, the resonance between Vedic cycles and modern cyclical cosmologies is impossible to ignore. They each invite us to see beyond the concept of a lone creation event, suggesting an endless tapestry where the universe arise and fade like tides upon an infinite shore. We've journeyed through ancient Vedic visions of timeless cycles, and modern theories of repeated universes, each echoing the possibility that we're part of an ever renewing cosmos. Now, as we approach our conclusion, let's pause to reflect on what this means for us today and for future discoveries. Our daily routines often make cosmic cycles feel distant, but just as night follows day, perhaps entire universes follow one another in the grand scheme of existence. In Vedic thought, these cycles underpin not just the cosmos, but life's moral and spiritual arc, reminding us that endings are beginnings in disguise. Science and spirituality, while distinct, converge on this one profound point. The cycle of creation and renewal shapes not just the stars, but our understanding of life itself. Whether we approach this from complex equations or scriptural verses, both paths lead us to wonder, could the next cycle already be etched in the fabric of space-time? Might our cosmic ancestors have left subtle imprints waiting to be discovered by advanced telescopes? These questions drive scientific endeavors and fuel spiritual reflections, hinting that the boundaries we draw between old and new, science and faith, might be far more permeable than we once believed. Even as we strive to decode the universe's origins, we find ourselves part of a much larger narrative. One day, our technology may confirm or refute cyclical models. Until then, we hold a unique vantage, melding age-old insights with the tools of modern science to peer deeper than ever before. This shared quest unites humanity across culture, creed, and discipline. It's a quest not just for facts, but for meaning. In the end, cycles in the cosmos mirror the cycles within us: birth, growth, transformation, and rebirth. Thank you for joining us on this extraordinary journey from ancient Vedic cosmology to the cutting edge of modern physics. If these ideas kindle your curiosity, please share this episode, subscribe, and let us know your thoughts in the comments. Until next time, keep your eyes on Bharat. Keep exploring, and remember, in a universe that may repeat forever, our quest for knowledge is never truly complete.